Hello, AP Stat students. Mr. Hazelhorst here with your Chapter 6, Section 3 video. Today we're going to expand on the probability rules that you learned in the first video, and we're going to learn a whole bunch of more formulas that we can use in calculating probabilities. And the focus is going to be on probability rules that involve unions and intersections. So we kind of introduced those symbols in the first video and kind of briefly mentioned them, so we'll kind of break those down into more detail today. And again, look at quite a few formulas that we can use in calculating probabilities. So let's begin with unions. All right, we mentioned this the other day. We said a union is a collection of events, is the event that at least one of the collection occurs, right? So we said when you think union, I want you to think the word or, okay? That's what we mean by at least one. If I say stand up if you are a freshman or a senior, you don't stand up if you're both of those. You stand up if you're at least one of those, right? And again, that's the word or. The other day in our first video, we learned rule number 3, which was the addition rule for disjoint events. All right? It said if we're finding the probability of A or B, we just take those probabilities and we add those together, okay? Now, again, we need to specify that this rule only works if the events are disjoint or mutually exclusive. If you think of the Venn diagram, remember they're going to have two areas that do not overlap at all. A and B have nothing in common, okay? So we're going to expand on that rule today to begin with. So let's just look at an example problem, all right? It says, what is the probability of drawing a face card or an ace from a standard deck of cards? Now, the first thing that we need to address in this problem, what I have learned in my years of teaching, is that the knowledge of students when it comes to a deck of cards has decreased greatly. So we first need to make sure that everybody understands what is meant by a standard deck of cards. We're going to use this phrasing quite a bit in this class, and I'm going to take the assumption that you understand what is meant by a standard deck of cards. So let's discuss the details here real quick. Here I've got a diagram representing a standard deck of cards. All right, you can see that these cards are divided into 4 separate suits: heart, diamond, club, and spade. Within each suit, there are 13 different cards. All right, so in total, there are 52 cards in a standard deck. We do not include jokers in a standard deck. All right, each suit contains numbered cards 2 through 10. And then we have what we refer to as face cards, right? The J represents a jack, Q a queen, and K is a king, right? Typically, if you're playing with a deck of cards, those cards are referred to as face cards because they have the faces of people on them. And then the last category of card is we have an ace, all right, which is just represented by a letter A. So those are the 52 cards within a deck. Notice that the hearts and the diamonds are red, clubs and spades are black, and again, representing a standard deck of cards. So in this problem, we were asked, what is the probability of drawing a face card? Now there's that word, or, so we don't have to be both of them, we just have to be one of them, or an ace from a standard deck. Well, with the diagram, it makes it really easy to kind of draw this out, right? So we want to find a face card. Well, here's our face card groupings. Right, if we look at the face cards, the probability that we select a face card is 12 out of 52. Then we can take the ace part, right? We want a face card or an ace. Well, as I look at the diagram here, the probability of selecting an ace is 4 out of 52. Now, what our addition rule from the first video told us is that if we want to find this probability in an OR setting, we can simply add their probabilities together. And that's appropriate in this problem because they are disjoint. They are mutually exclusive. When I look at the circles that are drawn here, those circles do not overlap at all. Face cards and aces are completely separate of each other. So our probability ends up being 16 out of 52. Now, as we represent probabilities, there's multiple ways we can do that. One is through a fraction. However, if you're going to utilize a fraction, my preference would be that you reduce that down to its simplest form. So we could reduce this down to 4 out of 13. That would be our probability of selecting a face card or an ace. All right, and we can see that that addition rule works great, okay? But how about a problem like this one? All right, what if we were asked, what is the probability of drawing a face card or a heart from a standard deck of cards? Let's go about it the same way to begin with, okay? So again, we want the face cards. So I'm going to erase this blue circle, leave the one in green there. All right, so here's our area representing the face cards. And then this time we want to find or a heart. Now, what do you notice about our diagrams in this setting compared to the first problem? Well, hopefully what you recognize is these circles now overlap each other. What that means is that they are not mutually exclusive. So the rule that we learned in the first video and that we looked at on the previous slide doesn't apply in this problem. Right? But with a little common sense and a little intellect, I think we can figure out the rule. Most of you have probably seen this rule before because you've studied probability in other classes. But let's take a look at it. All right? So what we're going to do is we're going to start out the same. All right? We're going to add the probabilities of face cards and hearts. So face cards, we know, we already said that up above. Probability being a face card, 12 out of 52. We're going to add to that the probability of being a heart, which is 13 out of 52. However, I want you to recognize if we added those probabilities together, there's a group of cards here, the Jack of Hearts, the Queen of Hearts, and the King of Hearts, that would be included in these numbers twice. Right? Those three cards were included in the number for the face cards and also included in the number for the hearts because, again, these events are not mutually exclusive. So what would it make sense to do with those numbers or those cards? Well, hopefully you say, well, let's just subtract it out. And if you thought that, that's exactly what our rule is. Okay? So what we end up with here is 22 out of 52 cards would represent being a face card or a heart. And if we count those up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We can see that makes sense in that context of that problem. All right? But again, representing your probability is a reduced down fraction. So this would be equal to 11 over 26 if we wanted to reduce that down. All right? Now, what we just demonstrated in this problem is what we refer to as the general addition rule for two events. The first rule that we covered with regards to addition and using the union or said, well, if they're disjoint, you just add them together. What we're saying now is they don't have to be disjoint. All right? If we have a setting where those two areas overlap each other, and that's what we see in the diagram down below here, right? A and B share a common area. Well, we can still find that probability very easily, right? We add the two individual probabilities and subtract what I like to refer to as the overlap. Now, if we want to get technical, we would refer to that as the intersect area, and we see that represented in our formula here. Now, I do want to point out that this formula is in your gold packet, all right? So not a formula that you need to memorize, but a good thing to be aware of, all right? So that is our addition rule, again, for the union of two events when we're utilizing that word or, and it works in all kinds of different situations, okay? So let's move on to our next formula, okay? Oh, before we get to that formula, I want to talk about diagramming probability models, okay? And this will be a helpful tool. I know some people tend to struggle with probability, so if we can equip you with some different tools to use, that's going to help you as you deal with these different settings. All right, so let's do that here. So in this problem, it says Zach is applied to both Princeton and Stanford. He thinks the probability that Princeton will admit him is 0.4. The probability that Stanford will admit him is 0.5, and the probability that both will admit him is 0.2. So we're asked the question, what is the probability that neither university admits him? And then we're also asked the question, what is the probability that he gets into Stanford but not Princeton? All right. So again, we've got some different situations to deal with here. Now, this is an example where utilizing a Venn diagram is a helpful way to help us answer probability questions and represent the sample space of the situation.
There is coffee now available in the concession stand in Olive Champions.
All right, we'll ignore Mr. Nienhauser for rudely interrupting our video there. There is not coffee available for you, by the way, unless you go down to your kitchen to make some. All right, back to our problem, though. So let's draw a Venn diagram to represent this situation. So what we're going to do here is we're going to begin by drawing a box. And this box is going to represent the sample space of this situation. The next thing that I want to do is I want to represent the events that I'm dealing with. So I'm going to use the letter P to represent the probability of him getting into Princeton. And I'm going to let S represent the probability of him getting into Stanford. Okay? Now, as I look at this problem, there is a probability that both admit him. So it is possible that he gets into both of these universities, which means that they're not disjoint or they're not mutually exclusive. So as I draw them into this diagram, I'm going to draw them with an overlap area. So we're going to let one circle represent Princeton and one circle represent Stanford. Now I'm going to get rid of the S that's up here in sample space so that we're not utilizing multiple variables. Okay? Now at this point, we can get really detailed with what each area of this diagram is representing. When we draw it up here, you can see there are 4 different areas. We have this kind of moon shape that represents Princeton only, this moon shape that represents Stanford only, the overlap area, and then what's outside of those 2 circles. There's 4 different areas in this diagram. And we could describe them using probability notation. All right, so let's start in the intersect area. We know what that means. That's the intersect of those. That means he's getting into Princeton and Stanford. Now, if I go to the P circle, right, taking away the intersect, this area would mean he gets into Princeton, but not Stanford. And when we say not Stanford, that's representing a complement. And so we can represent that by taking S and superscripting a little C up above it. So what this notation means is, all right, this is the area that's probability and not Stanford. All right, the second area would be not Princeton and Stanford. And then the last one is not Princeton and not Stanford. All right? Now, using the information that we're given, we can go back and we can assign some numbers to these areas. So, let's begin. All right, where I like to start is in the intersect area of the probability, and we'll expand out from there. All right, so the probability that both admit him is 0.2. All right, so I'm going to label that in the intersect area. Now, as I go back through the problem, they tell me the probability that Princeton will admit him is 0.4. Now, when I look at that, Princeton right now is being represented actually by 2 areas, right? This entire circle here is representing Princeton. But we already have a number within that circle, right? Probability of Princeton and Stanford is 0.2. So if that total circle is worth 0.4, that means all I have left for this area is another 0.2. Okay? Now, some of you might think, well, shouldn't that moon shape just be 0.4? We'll go back and address why that can't be the case here in just a moment. Okay? So then we go to Stanford, right? Again, the Stanford circle would be represented here. Again, made up by a combination of 2 areas. We already have 0.2 in that circle, so that means this area has to be 0.3, so that total circle is equal to 0.5. And then finally, we have the area that's outside of those 2 circles and their intersect area. So the probability that he doesn't get into either college, well, we already know that if this is truly a sample space, all the probabilities have to add up to 1. So this would be 0.3, right? 0.3 plus 0.3 plus 0.2 plus 0.2 equals 1. We have all 100% accounted for here. And now I can use this diagram to answer these questions pretty easily. What is the probability that neither university admits him? Well, that'd be outside of those 2 circles. So that probability is 0.3. And the probability that he gets into Stanford, but not Princeton, Well, that's this little moon shape that we drew right here, which is also representing 0.3. Okay? So sometimes it's very useful to diagram out a probability setting and then use that to answer questions. All right, let's move on next to some rules regarding the intersection. All right, we covered the addition rule and unions, so now we want to move on to the next part. So intersections, again, that's relating to the word and, right? That's the area where, as we look at the last diagram, where those events overlap each other, okay? So we're saying the intersection of any collection of events is the event that all the events occur, right? So if I said stand up, if you're a senior and a male, all right? Well, that means you have to be both of those events in order to stand up. Some of you watching this video, you're seniors, right? Some of you that are watching this video are males, and then some of you are both of those. But you only get to stand up if you're both of those, right? That's the word and. And again, the symbol that we use for that looks like that upside down U. Now, yesterday, or in the first video, I should say, we talked about the multiplication rule, right? We said if A and B are independent, okay, and again, remember, different phrase than disjoint or mutually exclusive. Independent, again, means that the probability of one event will have no impact on the probability of a second event, all right? So those probabilities are not changing based on what occurs before it. So those are independent events, all right? And if we have independent events, we can just simply multiply their probabilities together, all right? So let's break this down into a little bit more detail. So let's say we have a bag that contains 10 marbles, all right? 4 of those marbles are blue, 6 of those marbles are white. So the question is, what is the probability that you select 2 blue marbles out of the bag? Okay. Now we're going to look at this 2 different ways. First is if the first marble is replaced, the second one if it's not. Now, think about that for a moment here. What does that mean when it comes to replacement, right? Well, if I replace the marble back in the bag, that means that these events are independent, right? The second draw of the marble, that probability is not impacted by in any way by what happens in the first marble if it is replaced. However, if we do not replace the marble, then the second probability has now become dependent on what happens in the first. So let's think through how this might affect our probability situation in calculating the probability, all right? So again, we want to select 2 blue marbles. That would mean the first marble is blue and the second marble is blue. That's how we get the and word in there, the intersect. Right? Now, again, we said the first one, they are independent, so all we have to do is multiply their probabilities. So the probability that the first marble is blue would be 4 out of 10. The probability that the second marble is blue remains 4 out of 10. Because again, the first marble is put back into the bag. All right? So in both selections, there's 4 blue marbles in the bag and 10 marbles total. The probability, again, unaffected by what happened on the first selection. So this would come out to be 16 out of 100. We could reduce that down to 4 out of 25, or we'll say that's 16%. Okay? Now the second question says, okay, what if this time we don't replace the marble? Well, the first probability isn't changed at all, right? There's still 4 out of 10. So what are we going to assume happens in this situation? Right? Well, we have to assume that we selected a blue marble. That's the only way that this situation is met. All right, so let's pretend, okay, we selected a blue marble and we're not going to replace it. Well, how many blue marbles are left in the bag? Well, there's 3. How many marbles total? There's 9. Right? So again, that probability was influenced by what happened in the first one. Right? They're now dependent events. Okay? But again, we're just going to multiply these together. So we end up with 12 out of 90, which would be approximately 13%. Okay? Now again, a little common sense, a little logic, and we're able to see, hopefully that makes sense to you, why we would multiply 4 tenths and 3 ninths. Now we can formalize this in a rule. And this is what we refer to as the general multiplication rule. And the general multiplication rule says, all right, if we have events that are We could say dependent, okay? Now we have some tricky notation here, okay? So we have the probability of A intersect B, right? So think of that as the probability of A and B is equal to the probability of A. So we take our first event. All right, now here's some new notation. All right, we would read this as the probability of B, and then this vertical line is read as a bar. So we can read that as the probability of B bar A. Now what a bar means in probability settings is given. All right, what we're essentially saying is what is the probability of B given A? Now go up to our marble situation in this problem. All right, what did we have to be given in the first selection? Well, it had to be a blue, right? And we factored that in as we calculated this probability, okay? So we said, okay, here's the probability of A, 4/10, probability of selecting a blue marble, right? And then the second number is the probability that we get a blue marble given that the first marble is blue. Again, it's dependent on what happens before it, right? But still, it boils down to multiplication. All right, whether I replace it or I don't replace it, I'm still just using a simple multiplication rule. All right, the difference between the first problem and the second one is the second one we had to factor in what happened on the first poll. Right? Hopefully that seems pretty simple to you. Okay, and we'll get more practice with this in class as well. All right, but we can expand to some different rules as well based on this formula. All right, when we create this general multiplication rule, we add in this conditional statement. Sometimes we might want to find what we refer to as conditional probability. All right, so maybe that's what we're being asked. What's the probability of B happening given that A already has? Now, this formula is found in your gold packet. And so you can look there. You'll see it's right by the formula for the addition rule in general. And so again, not a formula that you need to memorize, just one that you need to be able to use. Now, what we need to point out here is that B is representing the event whose probability that we're trying to find. But we recognize that B's probability is dependent on what happens in A. So A is what we refer to as the given information. Okay? So let's go back to our problem with Zach and applying to Princeton and Stanford. So again, we have this same information that we looked at before. And the question that we want to ask this time is, what is the probability that he gets into Stanford? And then notice the phrasing, given that he has already been admitted to Princeton. Okay? Now, let's go back to our previous slide here. So I'm going to end the show, and we're going to go back to our diagram that we created earlier. If I can get up there. All right. And so let's pull this back up. Okay? So again, the question is, what is the probability he gets into Stanford given that he has already gotten into Princeton? All right? Stanford given Princeton. All right? So essentially what we're going to do in this problem is we're no longer looking at the entire situation, right? We now know something. And when we know something, that narrows down our probability. And so I'm going to ignore basically all of this diagram because now what I know that he's gotten into Princeton, right? So I don't have to worry about him not getting into any college. I'm not worried about anything else, right? So we take that entire diagram and we shrink it down to the given information from the setting. And we were given that he was admitted to Princeton. Okay? So, right, that's only 40% or 0.4 of the entire situation to begin with. But that's all that we care about in this problem. All right, when we're given something, that narrows our scope of what we're dealing with. And now from here, we're going to answer, well, what's the probability that he gets into this region, right, knowing that, again, he's in Princeton. We know that he's in the Princeton circle. So now what's the probability that he can get into the part that includes Stanford? Well, it's very simple, right? We take 0.2, the probability of Princeton and Stanford, and we divide it by the total of the circle, which is 0.4. And what we find out is his probability is 0.5. All right? So the probability that he gets into Stanford, given that he was already admitted to Princeton, is 0.5. Now notice that that didn't change from the original Stanford number. And that means something important to us. So let's go back to our previous slide here. Let me close this out. And we'll skip back ahead. All right, so what this means, since that number stayed the same, is that Princeton and Stanford, him getting admitted into those colleges, were independent of each other, right? The fact that he got into Princeton didn't impact the fact that he got into Stanford, because the probability of B given A, which we just calculated to 0.5, was the same of him just getting into Stanford of 0.5. So these events are what we refer to as independent, okay? And that's just a way that mathematically we verify that things truly are independent, is when their probabilities remain the same regardless of what's given to us. And that's what we see here, right? We were given that he was admitted to Princeton, but that didn't change his probability of getting into Stanford, okay? All right, well, let's deal a little bit more with this idea of given and how we narrow that down. So a lot of times we'll deal with probabilities from a table setting, right? So here's just a basic probability question. What is the probability that the person you choose from this set of information, right? Here we have information of workers that have different levels of degrees. So we have bachelor's degrees, master's degrees, professional degrees, and doctorates. We have them broken into two different genders, male and female. We're going to use this information to answer some basic probability questions, okay? So the first one says, what is the probability that the person you chose is a woman? Right? Well, if I look at this here, in total of this table, there are 1,119 women, and there are 1,944 people total, right? So simple probability question, 1,119 divided by 1,944, and we can see this would come out to be approximately 57.6%. All right, simple, okay? Now let's add in the conditional part. So let's change the question. All right, it says, what is the probability that you chose a woman given that the person received a professional degree? All right. Now, once they add in this given statement, that should narrow the scope of what I'm looking back. Think back to our previous problem. I erased everything around what we were given. Well, in this problem, since I'm given that they have a professional degree, that's the only part of the table that I care about. I'm only going to look at these numbers. So let's answer the question out of that subset of information. So the probability that you choose a woman is 39 out of the total number of professional degrees, which is 83. Right? So this would come out to be approximately 47.0%. Okay? Now we can piggyback off of that last slide that we just looked at in verifying independent events. If we compare these two probabilities, right? Here is the probability of selecting a woman at whole. Here is the probability of selecting a woman given professional degree. Now, because these probabilities are separate, what that tells us is that female and professional degree are not independent events because those probabilities change. Okay? So again, that's a concept that I'm going to have a feeling we'll have to hit on a little bit more. And if it isn't clear to you, again, leave that in the comment box. All right? So last question here. What is the probability that you choose a person with a professional degree given that they're a woman? Now, the reason why I want to do this question is notice I'm dealing with the same two situations as the previous problem. I have woman and professional degree. Here I have professional degree and woman. But what's changed in this problem is what was given. Right? Previously, we were given professional degree, but this time we're given that they're a woman. Okay? Again, whatever I'm given narrows the scope of what I'm looking at. So last time we were given professional degree, so we focused in on this circle, but now we're given female. So we're going to look at this subset of information, and we're going to answer our question off of this. Okay? So in that area, what's the probability of having a professional degree? What would be 39 out of 1,119, which would come out to be approximately 3.5%. Okay? So again, as we deal with conditional probability, when we have this given statement, what we need to recognize is the fact that that narrows down the information that we're looking at. We're not looking at everything that we have available, but we're only looking at what we're given, and we're going to answer our question off of that. All right, well, I hope that made some sense. If not, as always, I want to encourage you to fill out the comment form below. Again, as always, mark your level of understanding, and if there's anything specific from this video, please make note of that so we can tailor the lesson that we need to cover on Wednesday in class, specific to the questions and concerns that you still have. Well, I hope you guys are having a great day, and I hope you continue to have a great day, and I will see you soon.